Okay, so let's start doing some drugs. Who wants to do drugs? Woo! We all do. 8:30 p.m. to 9:30 p.m. Let's do some drugs. Hopefully, this really is an interesting class. Hopefully, we're not all on a list somewhere right now. So specifically, we're going to talk about the drug PCP. So this is short for Post Correspondence Problem. So yeah, we're not really going to talk about drugs, but this proof is so cool, you might as well be on them. So the whole, I don't know if I can get through the entire proof, but I want this to be an interesting thought exercise as to think about decidable and undecidable doesn't necessarily have to be just with algorithms or with not algorithms, with machines like Turing machines and whatnot. Decidable and undecidable can live within puzzles and games. So, for example, there was a paper that was published like 5 years ago that showed that the hardness of, say, Super Mario, so like being able to show that that game is actually difficult to actually solve. So a lot of recent work has been on looking at a certain game and figuring out how hard is this game to solve in a generalized context. So like Sudoku or checkers or chess or all that sort of thing. This is an early problem in that kind of domain. So here we're actually going to be given a bunch of what are called dominoes. So if you recall, a domino has two sides, but we're only going to look at one side, but it has two faces on it. So the domino here is going to be something that looks like this. So this thing is a domino. Let's all order dominoes. Sounds good about now. Yeah, so this thing is a domino. And we could have a collection of dominoes. So we can have a set of them like this one. And so I'm just going to follow the book on this one because they have really good examples. So let's just say we have this. And then we have this one. Oops. So this is just a collection of 4 dominoes. And what we're going to do is I'm going to allow you to have as many of each of those dominoes as you want. You can have an unlimited amount of each of these dominoes. But what you can't do is flip the domino over. You can't like rotate it or anything. You got to keep the dominoes in the same orientation that you have them. So I can't flip like the first one to have the CA on top and the B on the bottom. I got to have them in this order. And our goal is to pick some of these dominoes really in any order we want, such that if we have the dominoes laid out in some order, we read the string off the top of them. So we just concatenate all the strings on the top and all the strings on the bottom. Then the strings are the same on both pieces. So the top string is equal to the bottom string. So what do I mean by this? So let's say that I'm going to color code this to make it easier. So I'm going to call the first one blue, the second one is red, the third one is green, and the fourth one is purple. So one way we could arrange these dominoes and pick some number of them so that the top string is equal to the bottom string is to do this. So I pick the 2 domino first, and then I pick the 1 domino, and then we pick the 3 domino, the green one, And then we pick the second one again. So again, we can have as many of each as we want. And then finally, we have the purple one. So if we read the top string, if we just read across the tops, we have A, B, C, A, B, C. If we just read across the top. So this is the top string. And then the bottom string is A, B, C, A, B, C. So they really are the same. Because if we just string the strings on the top, we put them all together, it's the same string as the ones on the bottom. Okay, does everyone understand why that is? So this thing, when we have this is called a match. So in other words, the set of dominoes that we have has a match because we have some way of picking these tiles out of here, these dominoes, and then stringing them together to make the same string on the top and the bottom. Okay? Any questions on what the problem is here? Yeah.
So you can repeat it as many times as you want?
Yeah, I can repeat any of the tiles as many times as I want. Yes. Yeah, so we have an unlimited number of each of the tiles. Any other questions? Okay, so let's look at this set of dominoes. So let's just say we have ABC over AB and CA over A, and then ACC over BA. Does this one have a match? No, why not? What's a quick proof?
So there's
Actually, yeah, that's actually a quick proof. But what's another proof? Right, yeah. So the lengths of the strings on the top are always bigger than the ones on the bottom. So when I put the first tile on, I'll never get a shorter string on the top and the one on the bottom because I can't rotate the tiles. Everyone see why that is? Okay, let's do a quick warm-up. So, let's look at this problem. So let's call it silly PCP, which is all tiles have the bottom, bottom length bigger than the top length. Or the top bigger than the bottom. It doesn't matter here. So is this problem decidable or what?
Yes.
It is decidable. Why is it? Because the answer is always? No, of whether the tiles have a match. What is the answer always in this case? Is always no. It's always no because there's no possible way for the bottom to match the top because the bottom is always bigger than the top. So this is decidable. So the question is, what about like the unrestricted case where we have anything on the top and anything on the bottom? So let's define the problem. Just normal PCP is just instances of the post correspondence problem. And P has a match. So what's actually quite amazing is that this is undecidable. may think, wow, like this very simple game, this very natural, well, maybe not natural, but this very easy to state and understand game is undecidable, which is actually quite amazing. So yeah. So how would you actually prove that? How would you actually show that this is undecidable?
It doesn't ever project
What doesn't?
the actual PCP because it'll, like from the game, it'll, I guess, only be accepting. It's never projecting because it's just going on.
Yeah, but in some cases, like this one, there may be no possible match, and in some cases, there is a match. So notice that we could have really, really long chains of tiles because the start might fall behind and then it might catch up again with a really long tile on the front. So it may actually be really hard, and we can have an unlimited number of each of the tiles. So it's not like we can just enumerate all possible orderings of the tiles because we can have an unlimited number of each. So that doesn't show, of course, that it's undecidable, but it's harder than just enumerating everything. So whenever you see a problem like this, where you say, okay, we have something that can't be solved, how did we approach it before? Assume it is decidable, and then what did we try to do with the supposed decider? We then tried to solve what problem, for example? Andrew?
All DFA. Something like that.
All DFA is decidable.
One that is undecidable.
The one that is undecidable. What is the prototypical undecidable problem? The prototypical one, the first one we did. ATM. Yeah. So if we can encode a Turing machine and an input simulation using tiles, then if there's a match, then that would encode that the Turing machine accepts the input W. So if we can encode it into that, then we're okay. So we're actually going to do a different version of the problem, which is almost the same. Maybe we'll get to the detail of why there's a difference. So MPCP, So this is called the modified PCP, where, if I can spell where a given tile TB, so some tile must come first. So with the unrestricted one, we can have any, yeah, go ahead.
Just a side question, the PCP, would it be decidable if you could only use each tile like once?
Yeah. So if there's any restriction at all on the quantity of each of the tiles, we can just enumerate all possibilities and check if any of them are a match, yeah. It's just that because it's unrestricted. So it's kind of like the LBA situation, where if we restrict it, then we could just look at all possibilities. The same idea here. But just because it's unrestricted doesn't imply undecidable, of course. But it is undecidable. So let's look at something called the modified post correspondence problem, where one of the tiles I'm going to tell you have to use first. So like for the example that we did before, if I told you that tile 2, the one in red, you have to use that one first, then of course there's a match now. If I told you that tile 1 has to occur first, there may or may not be a match. So I'm telling you that there is a specific tile you have to use first. Specific domino you have to use first. Okay? And we'll show that MPCP is undecidable too. So why do you think we're going to talk about the MPCP first? We may not get to the full one, given how much time we have, but how would you why do you think that we enforce a given tile first? Yeah, eliminate possibilities, but if we're trying to simulate a Turing machine on an input, what must the Turing machine start with? The start config. So the reason we're doing this is to enforce that the start config starts first. And so that's why it works. And in fact, if we didn't make that restriction, then we could always, the answer will be always yes, because we're going to have tiles which have the top and bottom being the same. So if I didn't enforce you a certain tile to come first, then you could just use that tile and then you're done, because there's a match, from the top is equal to the bottom. But what's going to happen is we're going to have the top always lagging behind the bottom. So the bottom's going to be further ahead, and then at the very end it's going to catch up if the machine accepts the input W. Okay? So that's the essential idea. So we're going to proceed in stages. So I'm going to tell you what tiles are going to actually occur, or what tiles I'm going to provide you. So the first set of tiles, there's only going to be one in this case, which is the top is going to be a single pound sign to, it's basically like the configuration type business. And then the bottom is going to be Q0, W1, W2 through WN with the pound sign on the end. So it's just a single tile to get us started. Okay? And then the top is going to basically fall. It's already lagging behind, and then at some point it's going to catch up. So what's going to actually occur here? Well, let's actually look at it from a different angle. So what is happening right now is that I'm going to put a vertical bar where there's where one tile begins and another tile ends. So what we have so far right now is Q0, W1 through WN on the bottom, and it's looking something like this. And of course, this tile must occur first, as you might expect. Okay, so what's going to occur next? So the second set of tiles is if we have a transition, so now we're going to start modeling the transitions. Where we, actually I'll just draw it. A transition from state Q to state R, where we are, so we're reading an A on the tape and changing it to a B and moving right. Because this might be a transition that you see. You may see a right transition. Well, what are we going to add as a tile? So then we're going to add this tile, QA over BR. So why are we adding this tile? Look at what happens here. So notice right around the tape head. So if we're moving right, the only thing that really matters here for what the configuration looks like is that the where the state actually is and the character immediately to the right. And because we're only going to be moving right here. The rest of the configuration better be exactly the same. Because right around where the tape head is, that's where the changes are going to occur. So if we're only moving right, we only care about the next character around where the state actually is. And so what happens here is we're changing the A, which is the second thing in the top, to the first thing on the bottom, from an A to a B, and going from state Q to state R. So we're going to add that tile. And I'll do an example to showcase what this actually looks like. There's some qualifications on what Q can actually be here. I'm not going to delve into that because it's not really that necessary. The third one is if we have a transition that moves left instead of right. So same type of scenario where let's just say we're changing an A to a B and moving left. Well, if we're moving left, now we need to know the character to the left of us and to the right of us. Because the one to the right of us, that's the one we were looking at, and now we're going to change. But the one to the left, we're moving left, and then now we need to see that character. But here's the thing. The character to the left of us that we're going to see next, am I modifying it on this transition? No, we're only modifying the character to the right of us. So we need to add a tile, a domino, where the character to the left of us doesn't change. So we're going to add this tile, which is CQA over RCB. So I'm actually going to highlight the states here so that you can actually see it better. So Q's upstairs in the middle, and the state now is on the left on the bottom. So all we're really doing here is just modeling what the transitions actually are as dominoes. Yeah?
What do you add to the C?
The C here, I should have said. So the C here is any tape character. So for any tape character, I'm going to insert another one of these tiles. Yes. So C is irrelevant to the transition, but anything could appear on the cell to the left of us, so we need to account for that possibility. So for any tape character, I'm going to add one of these tiles where the C changes.
Let's say for the bottom two.
Yeah, so the C on the left on the top is the same as the C in the middle on the bottom. Yeah, because we're not modifying that character because it's just to the left of us. It's just now, after the transition occurs, we're going to see that character. So notice why we're doing this. The top. Think about what happened at the top. The first tile that we added was no configurations at all on the top and one configuration on the bottom. And every tile we've added so far is lagging behind by one transition. Okay? So basically the top is behind by one transition compared to the bottom. Because in the second one, we had QA, and then the next transition yielded BR. That was the next transition, or what happened afterward. In the CQA case, RCB happens after we apply a transition. So it's always one transition behind. And then at some point, we're going to have it catch up. But any questions on what we're actually doing here? Okay, yeah, go ahead.
Is the goal of this to try and make like the first one catch up to the second?
Right, so we got to have a match if it accepts it, so we're going to eventually catch up. Other questions? Let's do a simple tile to add as our fourth case. So we're going to add a simple tile, which is A over A for each tape character A. So for each tape character, we're going to add a simple tile, which is just the top with the bottom, being that one character. So why are we adding that tile, that domino? Well, the 2 and the 3 cases handle the area immediately around where the tape head is, or would have been, and that's obviously going to change possibly. But the rest of the configuration better be exactly the same from the transition before to after. So that part is exactly the same. So we better have tiles that have exactly the same character on the top and the bottom. So this is exactly why we had to have that one tile occur first. Because in the for case, just pick that tile if we're allowed to pick any starting tile. So if we just pick the for one, that's a match, and then therefore the answer is always true. So if we enforce that the first one is the first tile, then it gets more interesting because it's lagging behind. Okay. We also are going to add two other tiles. So we're going to add pound sign over pound sign and pound sign over blank pound sign. So why are we doing this? These two are for handling when one configuration ends and the next one begins. So if we have a configuration and we're just doing a normal transition, nothing special, then the pound sign is going to correspond from top to bottom. But what might happen is, let's just say we have a situation where we have something like this. We're at the very end of our configuration. So this is the configuration right now. Well, what happens if we're looking at this WN right here and we said move right one position? Well, what would happen in a normal Turing machine simulation if we're looking at some character, which is the end of, say, the input, and we went right one more? What happens? We get a blank character. So that's what the second tile here is for. It's saying the transition before is on the top, and then maybe we apply a right transition and we need an extra blank character, so the bottom is allocating the blank for the next transition. Okay, so let's actually do a concrete example first. So let's just say that so this is just an example. We have other tiles to add, but let's just do an example first. So let's just say that our string W is 0100. I'm just modeling the book here. The tape alphabet is 0, 1, 2, and blank. And let's say that Q0, there's a transition from Q0 to I'm going to deviate a little bit to make it easier, to Q1, which changes a 0 to a 2 and moves right. So the starting configuration is, the starting tile is always this one. No matter what the transitions are, this is the starting config. Well, it says, well, the second step right here, we have a right transition, so we need to add this tile, which is the state we were in before with the character we were reading before, then the character we changed it to, followed by the state we went to. Sorry, I need one more character in here because I need to have Q0 in there. My bad. So then we add the tile Q0, we look at the character we saw before, and then after we have the 2 and then Q1, because that's the tile that we added right here. So remember, the vertical bars correspond to dominoes that we're adding, tiles. So the Q00 to Q1 tile that we added was because of the right transition. What else? Well, because the 1 and the 00 that occur afterward are exactly the same, they never change, we can add those dominoes too. So we can add 1, 1 as a domino, 0, 0, and then 0, 0, And then, because we're at the end, we need to add the pound sign. Pound sign. We'll read the top and the bottom so far. Well, isn't the first configuration on the top and the bottom exactly the same? Right. Because the top models the previous transition and the bottom represents the next one, we're already okay, even though it's lagging behind a little bit. The part that the top is currently made so far matches the bottom from what is generated. The bottom has more, obviously, but it's matched everything so far. Any questions about that? But if we needed to add more space, of course we have the second tile for step 5 here. Okay.
So would we be given the diagram of Q0 transition to Q1?
What do you mean given?
Like, if this was a problem.
Yeah, so you mean like on a test or like in the general case?
Like in the general case.
In the general case, so we're trying to solve ATM. So we're given the input, the machine M and the input W. Then what we're tasked to do is to make the tiles from the machine and the input W. So we're just making the tiles. We're not actually constructing the match here. That's not our job. Once we make the set of tiles, we feed it to the supposed decider for this problem. And then it'll come back and say, oh, there is a match, therefore we can conclude that M accepts W, because there is actually a match. And if it doesn't, then we know M does not accept W. Okay, so what do we do next? So what we're going to do here is, for the 6th step, now we're going to have the top finally start catching up with the bottom. And it's kind of weird. Although this entire problem is kind of weird, but this one is especially weird. So for any tape character A, we're going to add 2 tiles. We're going to add a tile A Q accept on the top with Q accept on the bottom. And in the other order. So Q accept A over Q accept. So why do we add these? Well, if the bottom reaches Q accept, then obviously the computation's done. But does it hurt to have the configuration history not just stop at the Q accept, but whenever we have that last configuration, just repeat it over and over? Is that going to affect anything? No. So, like for example, so suppose that we have a configuration 0 Q accept 1. Well, I could, even though this wouldn't be the true definition of a configuration history, I could just repeat this as many times as I want. And then 0 Q accept 1, etc. So the whole point of this is to allow you to have the top finally catch up with the bottom. That's the entire point of these tiles. And then at some point, we're going to have it be that the top is still going to be generating things, and then the bottom is not generating anything because of the Q accept downstairs. So therefore, we're going to have, at the very end, we will have something like this. So at the very end, we will have something like Q accept between 2 pound signs. But the issue here is that it's going to be lagging still. So it's going to look like something like this. So it's still going to be lagging a little bit. So what we're going to add as the final step is a last tile. Although you don't have to use it last, the only way it'll work is if it's used last. So here it's going to be Q accept with 2 pound signs on the top and 1 pound sign on the bottom. The reason why we have the 2 and the 1 here is that one of the top and the bottom can't be empty. So in order for it to work, we're just going to put an extra pound sign on the top and the bottom. And then everything will match up at that point because we're allowed to repeat the accepting config, only the accepting one, as many times as we want to allow the top to finally catch up to the bottom. And then the final domino here is to have it exactly match up. And in fact, we can show now that this problem is undecidable. So suppose that the modified problem, the one where you're forced to have that first tile first, is decidable. Then we decide ATM as follows. We're going to have on input MW again, where M is ATM. Then, as our first step, we'll generate the set of tiles called P as before. Feed the set of tiles to the decider for the modified problem, supposing that there is one. If it accepts, then that means that there is a match, which means that there is a way to, there is an accepting config history. Because the only way that the top can match up with the bottom is if we end up with this last tile, which has Q accept in it. And the only way we could have gotten there is if each step along the way was a valid application of one of the transitions. So that's the only way we could have gotten there. If we started correctly and each of the transitions yielded the next config correctly, and we end with an accept one, therefore the Turing machine M must have accepted W. So we need to say accept here. And then if it rejects, we will reject. Oh, we may get to the original PCP problem. Cool. Okay, so I know this is really this is not an easy proof. The idea is easy, but the details are not. I understand that. The idea, which is more important, is can we actually simulate the Turing machine using these tiles in some clever way? That's the key here. The details aren't as important. The idea is important. Okay, so there's actually been a lot of work recently about some model that someone's wanting to study and showing that you can simulate a Turing machine with it, and showing therefore it's undecidable. So let's actually recap. We're looking at the modified PCP problem here, not the original one, where there's some tile that is that's marked where we have to use that tile first. You can't use any other tile first, but after the first tile, you can use any tiles in any order after that. So we had this be so that the first tile was actually, in general, the top was lagging behind the bottom by 1 transition. And the reason for that is for the second and third ones, which are to model the actual transition. So we need it to lag behind by one transition so that we can model the tiles for the transitions. So the first tile says, we're going to start with 0 configs on the top and the first one on the bottom, which we know what it is because we know what the start state is and what the input W actually is. So we can construct the first tile. Then for all transitions that occur, either we move right or we move left. In the case of moving right, the only character we care about is the next one after the state that we're looking at. And so, therefore, the only thing that will change is the state itself and the character immediately to the right of it. And so, if we have a transition of that form, we're going to add a tile which simulates that transition. And if we move left, then we need to know the character to the left of us. And that doesn't change from the transition before to the one after, so that's why the C is the same in both cases. But for every place that is not where the tape head is, either moving right or left, is always the same from the transition before to after, because we're only modifying right around where the tape head is. So we're going to add a bunch of tiles which are the same on the top and the bottom to allow you to account for those possibilities, because it's exactly the same. If we are looking at the configurations, we need to have the delimiters in between. Well, in the case of when we don't need additional room, we just have a pound sign on the top and the bottom, because we want to have the configuration's length on the top be the same as the one on the bottom. But in the case of when we do need extra room, in the case of moving right into the pound sign, we're going to allow you to put a blank symbol there. Remember, the top is behind by one transition compared to the bottom. So we did an example of this. And then at the very end, supposedly, because we don't have a transition out of the accept or the reject state, then once we reach the accept state, then the next tile cannot possibly be formed other than these two, because there's no transition out of the accept state. Okay, yeah. And then at the very end, we allow the top to finally catch up with the bottom, because once we reach the accept state, all we need to do is for the top to catch up to the bottom. And so we just have a bunch of tiles that allow you to generate a bunch of Q accepts in there to allow the top to catch up. And then at the very end, we allow you to, because it's lagging behind still by one transition, we need some final tile to make it all work. Okay, any high-level questions or general? Yeah.
Since this generates the configuration, I think, is that the decision to generate a configuration?
So here we're only making the tiles. We're not actually making the configurations. We have them in mind, but we're not actually making the tiles. That's what the supposed decider is supposed to figure out, whether or not there is a way of combining these tiles to actually generate one that has a match. But all we're doing is just making tiles here. So we're not actually making the configuration here.
Okay.
Other questions? Okay, so let's actually end on showing that the original PCP problem is undecidable. So the issue with just saying, oh, make the exact same tiles as you did before, and the proof will work exactly the same here, that's a problem because, as I mentioned, if we allow you to use any tile as the first one, then the fourth tile that we added already is a match, and so therefore we're already done. So if we want to show that the general problem is undecidable, where you can use any tile you want first, what we want is that we're going to coerce you into using a specific tile first. So you're allowed to use any one you want, but if you don't use a specific one first, then you're never going to get a match. And so that would show that PCP is undecidable. So what are you going to do here? So if we're going to show it's undecidable, let's do it this way. We're given an instance of the modified problem, and let's convert it into one for the general problem. So let's let these tiles be an instance of the modified problem. So I'm going to have a bunch of tiles, T1, B1, T2, B2, etc., up to TK, BK, B tiles from the modified, I'll do MPCP. And here, the tile T1, B1 was the starting one. Yeah. So we want to convert this to a set of tiles for the general problem. So here's what we're going to do. So let's let star be a character not used by any tile. So what we're going to do is, I'm again skipping over some details, but what we're going to do is generate these tiles. So we're going to have star, I'm going to have star on the top with T1, and then star B1 star on the bottom. And then after that, I'm going to have almost the same tile. I'm going to have star T1 again. Over now it's B1 star. And then after that, we're just going to have these tiles where one star is on the front and the second star is on the bottom at the end. Then we'll have star TK over BK star. And finally, what we'll have is a final last domino, which catches up at the end. So this, I'm actually showing you a proof that's not actually correct. There's some details here, but this is the idea. So you're allowed to use any tile you want, but if you use any of the tiles other than that very first one, you're not going to have the stars match up on the top and the bottom at the very front. So you can use any tile that you want, but it's just not going to work. You may notice that if we, for example, used this tile first, then used all of the ones but the first one, it would actually work. So there's some details that are missing here, like using a different character for that last tile. But this is the idea of being able to convert from one problem to the other just by putting a special symbol to indicate, well, if you don't use that first tile, there's no possibility you're going to get a match anywhere. Because if you use any of the ones in the middle other than that first one, then the stars aren't going to match up on the front. And so because of this, because we can convert from the MPCP to the normal one, that shows that the PCP is also undecidable. So these are for the general PCP. And so for that reason, PCP is undecidable. Yeah, there's no way I'm going to get to that. Any questions about this? Yeah.
I was just going to ask like a general question.
Yeah.
What would you use PCPs for?
There's not really much of a use for this because you can have as many tiles as you want. The key here is understanding that undecidable doesn't necessarily apply just to machines. It can be used for puzzles and games and like that. You had a question?
I forgot.
So you guys are going to really like me after I say this. PCP is not going to be on the final.
Thank you.
But I really want you to be able to see past the content of 355 of just machines and whatnot and see, oh, these natural games and puzzles are also undecidable. So with that, I conclude the material. I'll see you next Tuesday.